Okay, let's get started. So before we continue with the class, right? So some of you may have seen an email sent out by the president and provost office, talking about phase 3 and phase 4 operations and what that means for instructions. So from what I gather is that our course will stay as is. So it'll still be remote, right? All the labs will be remote. All the homework, the exams will be remote. So nothing changes with that respect. There is a note about having office hours being possible to in person. So we'll see what the department says about that. What if we get more guidance on that? Now, so if that's possible, and if you really want to see me in person and talk, then that's fine. But otherwise, everything remains exact as before. Right? So there'll be no change in the way the course runs. So yeah, so there's will be no required in-person activity from that email. It seems no matter what the status is. Right. So then with this class, so if you recall from last time, so we look at the recap. Right, so last time we talked a little bit about history of the power system. We talk about how it was developed, what was applications driving the expansion of the grid. Then we talked about AC versus DC. Right? We talked about AC versus DC. So we'll talk about what's the advantage of having alternating current versus direct current. So a clarification. So then this class will be AC circuits. So again, this should be things you have seen before, right? This should be what you have seen before, but this just a review and to put into a context of the power system, right? Which before you have maybe seen for low voltage circuits. Right? So here we're going to put into context for power systems. So the terminology clarification for us, we use a very loose definition of DC and AC. So what I mean is, so just for this class, okay, so again, this is only for this class. This is the notation. This is the terminology we'll use. AC means a sinusoid. So AC, we request to be, will almost always mean a sinusoid. For most circumstances, will mean a sinusoid. But then sinusoid, sometimes a periodic signal with zero mean. So what we mean here for AC is if you draw this out as it's either a sinusoid, something like this, or sometimes we'll take some signal like this to be AC. Okay, this is what we mean by AC in this class. So the sinusoid, that's as alternating current. If it's this sort of square wave, but has an average value of 0, often we'll take this to mean an AC wave as well, right? To mean AC wave as well. Then DC, right? So what does DC mean for us in this class, right? So if you normally, when you think of DC, you think of a of signal with a constant function value, right? That's what you normally think about DC. But for this class, when we think about DC, DC means any signal that is always non-negative. This is always non-negative. So what this means is, right, so this is a DC signal for sure. Or this is a DC signal because it's non-negative. Or something like this. Say I chop the AC wave, I chop the negative part out. These are all DC waves for us in this class. For this class, we use a very loose terminology for AC and DC. Right? So you think of AC as anything that's periodic with a zero mean, right, if you want. So DC just means something that doesn't have a negative part, mean DC. And the reason we talk about things this way is for this class, we don't want to go very much into filtering. So normally when you create a sinusoid, or when you create a straight line, a DC voltage, you need some capacitors and inductors as filtering elements. Right? You need to filter the signal. For us, we are not going to look at filtering very much. So for us, and always for AC and DC, what we care about is just the mean value, right, or the sign of the waveform. Okay. And this will become more clear as we go through this class, and when we get to power electronics, when we talk about DC signals. But it's good to have this picture in mind. As sometimes when we will talk about DC, that's not a constant, which is fine for this class. Right? So AC just means periodic with zero mean. That's most times a sinusoid, but sometimes there's other form of waveforms. And DC just anything that's positive is a DC value. Okay, so that's sort of something to keep in mind while we go through. Okay, so in previously use AC and DC to mean different things. For this class, that's what we mean by that. Then so now let's look at ideal AC waveforms, right? So what is ideal AC waveform? When we talk about AC wave, what kind of waveform, should we have in mind are the ideal ones that we have? Then the ideal AC waveform is a sinusoid, right? The sinusoid. We'll write V of t. You can think of this as voltage if you want. Okay, so if you want a unit on this signal, you can think of this as having a unit of volts, this being voltage. We write this as Vm cosine omega t plus a phase phi. Okay. So then this as a, right? So of course there's names for all these variables, right? So this is the, right? So we have F as the frequency. This omega, this is a Greek symbol omega. This is the angular frequency. This is the Greek symbol, right? So frequency, this is measured in terms of hertz, right? So angular frequency is measured in terms of radians per second. And then T is 1 over F. Anybody remember what 1 over F is called? Remember what T is called?
It's the period.
Period, right? So this is the period. And okay, so this phi, this is called the phase angle. Okay, so this is how, where your offset is. This is your phase, and then Vm, this is the amplitude. This amplitude. Okay, so this is our sort of ideal sinusoid wave, right? So this is a cosine wave or a sine wave with some amplitude, some frequency, and some phase shift. And so if you draw it out, it's a waveform like this. Right, so then the interesting thing, actually, if you look at this, right? Then something interesting happens is because in practice, most times the waveforms are never ideal. Okay, so in practice, the waveform is never ideal. An ideal waveform we can talk about as completely characterized, ideal sinusoid, completely characterized by amplitude, frequency, and phase. Right? This is how the three numbers that give you the full information about the waveform. But actually, in practice, our waveforms are just not that ideal. They are not all that ideal. Because if you actually measure it, for example, if you put an oscilloscope at your socket and wall socket and you measure the voltage coming out of the socket, right? Let's say you measure the voltage. Okay, measure voltage. This is a time series of your measured voltage. So if you actually measure it, it's sort of roughly sinusoidal, but there's sort of noise on top of it. There's actually a pretty noisy signal, something like this, right? It's actually a fairly noisy signal. So it's not a perfect sinusoid because there's a lot of noise, right? So it's not a very smooth function. Then if you measure a waveform like this, and you want to talk, then we want to say, okay, our voltage is 110 volts, something like that, right? But then if our signal is not ideal, then how do we summarize this voltage, right, for example, right? So if it's ideal signal, then it doesn't matter when you measure the amplitude, you got the same amplitude. Okay, so you can talk about amplitude as a number. Then for some signal that's non-ideal, for example, that has noise and goes up and down, things like this, then how do we characterize it? Right? The question is, how should we characterize it and how do we measure it? So then one suggestion we can have is, so we need to average. So basically, for actual signals, how do we characterize them? As we look at average values. Okay? We look at average values. This is how we want to characterize the signals. Because it's not ideal, so we need to average over some period to measure an average quantity to characterize them. Then for a signal like this, let's say we care about the amplitude, right? Let's say we care about the voltage amplitude. Can we measure average amplitude? Is that a good quantity to measure? Is average amplitude a good thing to measure? Why not?
Because it's going to be zero because you have positive and negative that are canceling each other out.
No, so average amplitude, I mean, as if you look at this signal, right? So amplitude is this VM, right? This is how tall the waveform is, right? So the peak value. So average amplitude meaning, should we just talk about sort of roughly what the average peak is? Is that a good thing to measure?
No, because it doesn't account for dramatic changes in data. So if there's a big outlier, it probably won't capture the actual information that we need.
Right, so the intuition is correct, right? So average peak value is very hard to measure because we don't know when the peak happens. Right? So we measure the average peak, you need to figure out when the peak happens. But then normally when you have an oscilloscope that's measuring, for example, in power systems, it's not taking a super high resolution measure. Right? So it's measuring maybe once a cycle or something like that, or a few times a cycle. Then talking about this average peak is difficult, right? Because there's not a noise. You don't know when the peak happens. As commented, if there's some outlier that may change the value quite a bit. If you just happens to have a big noise there, that will change your measurement a lot. So when you average, the first thing we have to figure out is when you average, it turns out average peak is not a good value to talk about. Okay? We don't want to talk about average peak value. So average peak value, we don't want to measure this So what we end up doing, the way we end up characterizing the signals is we define something called a RMS value. So we end up the way if you take oscilloscope, you plug into the wall, and you're trying to measure the voltage, how big the voltage is. What we end up measuring is the so-called RMS value of a signal. And RMS, just to remind us, this is a very good name. Okay, so RMS value is a very well defined name. So RMS, this is root, means square value. Okay. And it does exactly what the name says will do. Okay, so what this says is, if you take a V of t, think of this as a periodic signal. Period t. Then the RMS signal, root mean square, is basically it says that you take a root, okay, so root, you take a mean, and you square this thing. Okay, so this is what RMS means. So you square it, you integrate it, then you divide by t, that's taking a mean, and you take your square root out of this, right? So this is defined for all periodic signals. This is all defined for all periodic signals. And this is a fairly robust measurement, right? When you want to measure something, this is fairly robust. It's very robust to noise because you're doing integral, right? You're integrating the noise out. Okay? You're averaging, so you're not very susceptible to outliers, things like that. And this will give you a meaningful signal. This will give you a meaningful signal. Okay? So this is a very robust characterization. So when we talk about voltage, so for example, the 110 volts we say is the RMS value. Okay, so your house has 110 volts. What we mean is actually your house has an RMS value of 110 volts. Okay, so in this kind of periodic signals, in this kind of AC waveforms, we almost never talk about the peak. We very rarely talk about the peak of the waveform. So we very rarely talk about this VM value. Rather, most times we will talk about the RMS value. Because the reason is if you plug oscilloscope into the wall, the peak actually goes up and down all the time, goes up and down, depending noise and did something happen in the circuit. Whereas the RMS value is fairly robust. RMS value is fairly robust. So often most of the time when we talk about voltage, we're talking about the RMS voltage. Any question about this? Something to remember in your calculations. As the RMS value, when we in power engineering, almost always when we talk about voltage is this RMS voltage. Remember last time we talked about the voltage transmission lines. What we mean was this RMS voltage. That's what we mean. So let's do the calculations, right? In case, let's remind ourselves how to integrate the sine and cosines. So if you take a waveform that is, let's say, V max sine omega t, let's say we want to find the RMS value of this. So let's say we want to find the RMS. Okay, so let's integrate this. Let's try to integrate this. So before integrating, we take a square. So this is V max squared sine squared omega t. So obviously sine squared is not something that's easy to integrate. So anybody remember the trick for doing this?
Trigonometry.
Right, so you do a trigonometry. There's a lot of trigonometry identities you can look up. So for this class, you need to know the following trig identity. Okay, so we'll use this trig identity. This is sine squared as 1/2 1 minus cosine 2 omega t. Okay, so that's the trig identity we'll use. So there's lots of them. The others you can look up, but for this class, this one is required to know, because we often integrate sine squared. We often integrate sine squared out of this. Okay. So if we know this trig identity, then we can compute the average. Right? So root mean square, we did the square. Now let's take the mean or the average. But if you want to compute the average out of this, it's easier to just integrate over 2 pi for this function. Right? Instead of integrating 1 over t, since this thing is periodic in the cosine, it's periodic with respect to 2 pi, it's easier to just integrate over 2 pi and pretend omega t as a variable by itself. So this is V max squared over 2, 1 minus cosine. So we're going to pretend omega t as theta, d theta. So theta is omega t. When omega t completes 1 period, that means theta goes from 0 to 2 pi. D theta. You can integrate this out. There's no need to do this integral. But in here, we get V max squared over 2. We got V max squared over 2. And then we get the RMS voltage as the square root of V max squared over 2. So this is just V max over root 2. So this is how the root mean square value relates to the max value. It relates to the peak value of sinusoid. Any question with this calculation? Okay, so this is definitely something you expect to know. You'll see this a lot in the homework and in the homeworks. And in the midterm, we'll use this calculation a lot. So you should know, given a sinusoid, if this thing has a peak of V max, what is RMS? If it has VRMS, what is the peak voltage? Right, so yeah, go ahead.
Right. Since this is always true, do you, for homework and exams, do you expect us to show all these steps, or since we know that VRMS is always just Vmax over root 2, can we just do that and skip all the other stuff?
Oh yeah, you don't need to show the steps. This is something you expect to know very well. So you don't need to show the steps. You don't need to show those integration steps for the sine and cosine. You don't need to show this stuff. You can just this is the one equation you can directly use. Right. So again, because for the homework and the midterm and the final, everything's open book anyways, right? So you can Google stuff. So if we have done the steps here, there's no reason to show the step. So, but you need to know this as the equation to find. All right. So then the good follow-up question is, if I add a phase to this, does it change the RMS voltage? All right, so how about this? How about we add say this is instead of sine omega t, how about V max sine, let's say omega t plus pi over 3. How about this? Does the V max change? Sorry. Here, does the RMS value change? So I introduced a phase. No, right? The RMS value doesn't depend on the phase, because phase is shift when you cross 0 for a waveform. But you're integrating over a period anyways, right? Over one complete period. So the phase has no impact on the RMS value. So VRMS is still Vmax over √2. Okay. So that's good to know. Then how about, let's say, if we double VRMS? Sorry, if we double Vmax, then what happens? So let's say, right? So say, how about, suppose we get the VT as now Vmax. Let's say if I change Vmax by a factor of alpha, what is now the new RMS? Let's say I shift the peak by constant. And what happens to the RMS?
Should be alpha Vmax over √2 again.
Right, should be alpha, right? Just multiplied by alpha. So the alpha is now square. Right, so a common mistake is to square the alpha when talking about RMS. That's not square. Right, so this is alpha Vmax over √2. Okay, so this is the same. Then now let's look at, suppose this interesting thing happens. Let's say VT, this is Vmax. So now I double the period. Let's say I do this. Then what is RMS? Right, so this actually happens. This happens a lot. Because in the US, our grid is 60 Hertz. In Europe, it's 50 Hertz. In Japan, it's both 60 and 50, depending on where you are. Right? So the period is not constant in the grid. So does RMS change? Right? So if I take some device in the US has RMS, let's say 100 volts. Now I go to Europe with a 50 Hertz grid. Does my voltage, RMS voltage, suddenly change?
Yeah, it should, right? Because our integral only went from 0 to 2 pi, and with the period changes, then our integral should change.
Right, so this is the important thing to think about, right? Does it change, right? So it turns out this doesn't change. Right, it doesn't change. The reason it doesn't change, if you look at this integral, omega never showed up in the final solution. Okay, once you do the integral, the term with omega just went away. Right? So omega has no impact on the solution, and the reason it has no impact, let's look at this more closely as this. Okay? So if you look at this integral, okay, so we're integrating 1 over 2 pi, there are 2 pi, right? So before we are identifying, before we label as omega t, we're going to label to theta, and we're going to integrate over 2 pi period of theta. So if we change the period, we can always label 2 omega t as theta. We can always do this, right? So now we can do this. We get the exact same integral as before. We're changing how long the period is, but the period is divided out anyways in this equation. So if you change the period, this integral changes. That's true. If it would depend where you're integrating, but the length of the period changes as well. So this is something that cancels out. Okay, there's something that cancels out. So we do this integral. Let's do this integral carefully, right? So if you switch to theta, then you're always integrating 1 over 2 pi, 0 to 2 pi Vmax squared over 2 minus so 1 minus cosine 2 theta d theta. Right, so then we have Vmax squared over 2 because I'm integrating a constant from 0 to 2 pi. I'm dividing by 0 to 2 pi, so this doesn't change. 1 over 2 pi, 0 to 2 pi, cosine 2 theta, d theta. Why is this integral 0?
Because you're integrating over one period of cosine.
Right, integrating over one period of cosine, right? This integral is 0 because what you're doing is you're taking cosine and you're integrating over this one period. So it cancels out. This integral always cancels out. So this is V max squared over 2. Okay. So it doesn't matter, it turns out it doesn't matter what the exact the period is. The integral will always turn out you're just integrating over an entire period, or you're integrating over actually multiple whole period of cosine here. So it doesn't matter what the frequency is. So this RMS voltage only depend on the maximum voltage, right? Only depend on the maximum voltage. It does not, right? Only depend on the V max, not the other thing, not the phase, not the period. Any questions? What question about this?
Question.
Yeah, go ahead.
So when the period change is if the frequency, the angular frequency is 2W instead, it's 2W instead of the W?
No, because we're always
omega.
we're always integrating from 0 to 2 pi in this case, right?
So it's
So if
still
you-
a integration over a period then.
Yeah, it's always over one period. One period is it's in the angular form as 0 to 2 pi.
Okay.
Right, the angular form is 0 to 2 pi. So this is something to remember that for this kind of devices. So this is good. This is good for your computer. For any, if you want to charge a device at different places. Okay, so this is the voltage just depends on the peak voltage. And the reason we want to talk about RMS is when you measure stuff, you want to average out the noise. So this integral is very good at averaging out things. So we talk about RMS voltage for sinusoids. Other questions? Okay, so then if you look at our voltage, then if you plug all these meters into the wall, often what you measure is RMS voltage. So then the peak voltage, if your RMS is 120 volts, then the actual peak. So if VRMS is V max over square root 2. So here V max is root 2 times 120. This is about 170 volts. Okay, so the peak voltage coming out of the socket is about 170 volts. And the way it's important to note that often VRMS is written as V without any subscript, right? Just a capital letter V. Okay, so if it's not stated otherwise, V always mean VRMS. Right? So if you read some books or you read some menus, well, often the voltage is just V. So that means if not stated otherwise, V is the RMS voltage. Okay. So for example, you do your homework, the homework says V, just a capital letter V, is 50 volts. We're dealing with the AC waveform. Then you should take that to mean it says RMS voltage is 50 volts. So this RMS is used so often that we don't bother to write the subscript RMS. And so often to be careful, we'll write it. We'll write the RMS. Yeah, go ahead. Any questions, Alec?
So for the VRMS equals Vmax over square root 2, does that apply for all AC signals or just for sinusoids?
Just for sinusoid. That's a good question. Just for sinusoid.
Okay.
Right. The reason we got this equation is for this integral, and that's because we're dealing with a sign.
Okay, thanks.
Okay, so then, right, so that's a good question because that's up this fun. That's what I want to say next is you can define RMS for all periodic signals, but then our equation Vmax over square root 2 no longer applies, right? That no longer applies. For example, we can have a discrete waveform signal like this. Now here we can also compute what the RMS value is, but there's not a, the equation Vmax over root 2 doesn't apply. Here you actually have to do the integral and figure out what the correct value is. Here we have to do the integral. Okay, so we can always see, so here VRMS, this is always 1 over t, square root of 0 to t. V squared t dt. It applies to this discrete waveform, right? It applies to this discrete waveform. This is any periodic signal, you can do this integral, that's well defined. But Vmax over root 2 only works for sine and cosine, right? So that's the only time it works. If the homework or the exam asks you to find the RMS value of, for example, this periodic signal, then you have to do the integral. All right, so for example, let's do this integral. Let's see what this is. So if you do this integral, if you look at this waveform, what is the period for this thing? Before we integrate this, we need to figure out what the period is.
12.
Is this 12? Right, so let's look at the period, right? For this point,
yeah, 14, yeah.
16, right? It repeats at 10, right? So this is one period.
Oh, it's the
16, right?
it's different by 2 for each of the increment. I see.
Yeah, so different
Okay.
by 2, yeah. So the period is 16. Okay, so be careful of this. You will always get a question like this on the midterm to trick you. I think in every midterm for this class, there's a question like this to trick you to whether you account for the 0 in the signal values, right? So here the 0 counts, right? So here the 0 counts. Okay. Any questions about this? So here 0 counts, right? So then if you look at the VRMS, okay, so this is 1 square root 1 over 16. The integration of this is quite easy, right? Because all this are just square signals. So all you do is you just square them and add it up. Okay. So for example, this thing has height of 2, has a length of 2. So I have 2 squared times 2 for this block. I have now 4 squared times 2 for this block. 6 squared times 4 for this block. 2 squared times 4 for that block. That's all I have. Put it in, and this is 3.53 watts. Any questions about this one?
Wait, why is it 2 squared times 2?
Okay, well, it's good. All right, let's do this again. So if you look at this first block, right? So we're going to square this waveform, right? So the height of this is 2. Okay. Right, the height of this is 2. This thing has a width of 2. Right, so when you integrate this thing squared, this is 2 squared, right? So we're squaring V. Remember, this is V. We're squaring the voltage. So the height is 2. We're squaring it. So that's 2 squared times how long this thing goes on for, right? Because this is a constant signal up to for 2 periods of time, for 2 units of time. So this block is 2 squared times 2.
Oh, okay. Thank you.
Right. So for this one, for example, this thing has a height of 4. So this is the height is 4. You square the height, 4 squared, You multiply by 2, this is how long this thing go for. This has a height of 6, so 6 squared times goes for a length of 4 units in time, 6 squared times 4. And then this thing is 2 squared times 4. Other questions? Yeah, this is a good question to ask. You'll see this type of problems. You'll see this. So most of the class is sinusoids. But to remind you that RMS is defined for all periodic signals, in the midterm, you get something like this to integrate. You get something like this. And the most common mistake on the midterm or for this class on the homework is to just say Vmax over square root 2 for everything. So that's not correct, right? That only works for sine and cosine. So the level of integration you need in this class, you have to be able to integrate some constant value like this. You have to be able to integrate a straight line, right? For example, now it's fair to give you a question like this: what is RMS value of a waveform like this, right? So I expect you to know how to integrate the linear functions, constant functions, and the sinusoids because we gave you this equation. So I expect you to integrate these 3 types of functions. Right, so you won't be asked to integrate other form of functions, but you do need to know how to integrate a line, right? A straight line, a linear function, constant values, and sinusoids square. Okay. All right, so that's what we'll say about the RMS value of signals. So let's look like what happens when you're using a circuit, right? When using a circuit. So if you have a resistive circuit, if your VT is Vmax sine omega t, then the current through this circuit, this is Vmax over R sine omega t. Okay. So this is expected, right? This is expected. And we say that the voltage are in phase because there's no phase shift in the sine term. All it changed is the amplitude changed, right? All it changed is the amplitude. That's different if you go through in the circuit, but the phase didn't change. So we say they're in phase, right? It's just Ohm's law, right? Apply to this. Okay. So a resistor does not change the phase of the waveform, it simply varies the amplitude of the waveform. So that's expected. But things get a bit more complicated, right? So this is sort of this picture draw out as if you have a voltage and current that crosses the origin as crosses 0 at the same time. So there's no phase shift, there's no frequency change. So now let's look at what happens when you have an inductive load, right? So if you have an inductive load, if voltage is Vmax sine omega t, anybody remember what the current is, or how do we find the current? We'll have lots of inductors in this class, many inductors. I remember inductor equation. Have a sinusoidal voltage into an inductor. What is the current in the inductor? I remember the differential equation form for this. Okay, so this is LdI dt, right? The voltage across
I-
inductor is a derivative of current, right? Time
I
derivative
thought
current.
you were asking about the current.
Right, so this is how you find the current. You have this differential equation. Then how do you find the current?
Wouldn't that be the voltage though? Right? Because it's
So this, right, so the voltage
voltage.
relates to the current through this differential equation, right?
Then you
How do I find the current?
you can integrate.
Right, yeah, so we're gonna integrate and find the current, right? So this is current is 1/L. We're gonna integrate this voltage. So we're gonna do a indefinite integral. We're not going to worry about constants here. When you integrate this, you get 1/L integral of sine V max sine omega t dt. So this becomes V max omega L, right? Omega L. When you do the integral, this is cosine omega t. This is the equation we get for once we do the integral. So you will often see the inductor being labeled XL equals to the frequency times the inductance in the inductor. So this is minus V max XL cosine omega t. All right. Okay. So here we have a phase shift. Right? So V, T, and IT are not in phase. Right? One is sine, one is cosine, one is negative cosine. So they're not in phase. Right? So then, but they do have the same frequency, right? So omega never changed. So the frequency is always the same, but they're not in phase anymore. They're not in phase anymore. Any questions about this? Okay, all right. Then if you, so thing to remember is the inductor, right? The inductance show up as XL, the silent inductor. So if you take an inductor in the US grid, right, and now you move this inductor to Europe, as a 50 Hertz grid, you suddenly have a smaller inductor. Right? So the thing to remember, this XL is actually a frequency dependent value. Okay, so in the US, we have 60 Hertz, so that's omega. But then in Europe, we have 50 Hertz, so it's a smaller XL. Right? So that's something to remember. It's this XL depend on that. So here, just plotting out, right? So if you look at the two waveforms, one is sine, one is minus cosine. So here we say that the current lags the voltage by 90 degrees. Right? So the reason is if you look at the voltage here, the peak happens 90 degrees earlier. Okay, so we are not in phase for a purely inductive load. The phase difference is 90 degrees with the current leading it. The capacitor is a very similar story, right? So here we have, again, let's say Vt is V max sine omega t. Here the current is the derivative of the voltage. So this is omega c V max cosine omega t. We're going to call this, we're going to define xc as 1/omega c. So this is V max over XC cosine omega t, right? So again, out of phase. Same frequency. So it's similar to before. It's just in this case, right? So in this, it's a similar story to what we had before. Any questions about capacitors? So in this class, you see a lot of capacitors, inductors, and resistors. It's RLC type of circuits. So you put them all together, right? You put them all together. Remember is that the frequency never changes. So the omega is constant. RLC's loads cannot change the frequency. So that's always constant. But then of course you can have a phase shift, right? You can always have a phase shift. And our terminology is, right? Our terminology that here we say, okay, so if theta is positive, then the current lags the voltage. If theta is negative, then the current leads the voltage. Okay. Here we're going to restrict this theta to be minus 90 degrees to 90 degrees. Right, so normally the convention is voltage has angle 0 by convention, right? You can pick the reference angle. So voltage have angle 0. Then you look at the current angle with respect to the voltage. And depending on the sign of this angle, you decide whether it's lagging or leading the voltage. All right, questions about this notation? Okay, so if not, let's take our break now. Then after the break, we'll basically use the phasor notation, so we don't have to write the sine term or the omega t term every time, right? Since omega is always the same. Okay, so let's take a break until 3:34. Then we'll continue and talk about the concept of a phasor.
Could you go back one slide just real quick?
Sure.
Thank you.
Back to class. So if you look at the waveforms we've been carving, the signals we've been carving, right? Everything was sine, let's say, Vmax. Omega t plus a offset phi, then what you notice is this never changes. Okay, so omega t is carried all over the place. This never changes. So it becomes very inconvenient to write sinusoids every time. It becomes very inconvenient to write the sinusoid all the time. So then the way you do it is you want to summarize this into two parameters. Right? Only two things matter. The constant in front, Vmax, this may change from time to time. So this amplitude or this peak value changes time to time. And then you have this angle that changes time to time. That can change. Okay? So then when we summarize this two, we'll create a phasor. This is which basically just drops the sine omega t part, since that's always the same, and focuses on the amplitude and the angle, which we think of this as a complex number, right? So think. Okay, so much easier to think of this complex number, just for sort of economy of thought. Right? We can do this. So phasor is simple, is easy to work with because now I don't need to draw the sine and cosine waves anymore. Basically, the goal is not to draw this kind of picture anymore. It's to have algebraic way of doing calculations. And the phasor is something that essentially automatically does this for us, right? So if you think of phasor as a complex number, then a complex number you can think as a vector. Right, so a vector, complex number, we will think of as a two-dimensional vector. Then here, if you have a voltage phasor, so we're going to think of this as voltage phasor, then your current is aligned with the voltage. The current is in phase with voltage because there is no angle difference between the two. Okay, so these two vectors are aligned with each other. For a resistive circuit, right? So for a resistor, the phasors are the same. Then for a inductive circuit, there is an angle difference now in the two vectors. So what you have is you can have a voltage. Let's say this is a voltage phasor or the voltage vector, and then the current is 90 degrees out of phase, right? They create an angle of 90 degrees here. So this is our, for an inductor, this is the picture we have. And then for a capacitor, it's similar, just this time the angle is, I see, it's 90 degrees. So the current is 90 degrees ahead of the voltage. Any questions about this? So I'm assuming we have all seen this before, right? So if you have not seen this, please speak up. We'll go slower here. But this
That's
is
IC though. That's IC, not IL, right?
this, all right, IC, yes, that's right. That's IC, sorry. This is a capacitor. Yes, capacitor. So. Voltage. Okay, so this is for the three we have. Then for a mixed circuit, right, when you have RL and C, then the angle is not necessarily 90 degrees, it's some angle theta. Right, so here we can draw a voltage phasor, we can draw a current phasor. This is angle theta. This angle theta.
And so for that situation, is it always lag, or is there situations where it's a mixed circuit that it leads for the current?
Right, so this is a mixture that could be lag or leading. Here we're drawing it as a lagging, but it could be leading. Could be leading. Could be mixture, depending on which one is more dominant, right? Whether it's for more capacitive or more inductive. Right, so the angle could be positive or negative. There's the angle could be take both sides. That's right. Any other questions about this? Okay, so then since we said it's a vector, you can think this has a magnitude and angle. Now, of course, it's represented by complex numbers. Right? So the natural representation is complex numbers. So when you have a phasor, we'll think of as a complex number with magnitude and angle. Right? So it has a sine theta and a cosine theta. So so for us, the phasor is A with a bar on top. This is the phasor notation or a vector notation. Right? And we can write this as magnitude A with angle theta. This is fine. This is a magnitude angle notation. Or we can write this as A cosine theta plus J A sine theta. Right? So these three things are all equivalent objects. Right? It's a complex number A bar. It's a magnitude and angle, or it's a real and imaginary part. Okay? So this is all these are equivalent in some sense, right? So depending on which one we want to work with, there's different times or different forms that's easier to work with. Okay, so all these three are equivalent forms. Then if you look at the impedances, right? So a resistor, as the impedance of a resistor is still a real number, purely real number, right? Just R. There's no angle, so there's angle is 0. But then if you look at inductor, then what is the impedance here? Well, Ohm's law still holds. So this is V over IL. So bars here denote complex phasors. Right? So bars denote complex phasors. If you write this as angle, so angle 0 degrees. This is IL angle minus 90 degrees. And here you have V over IL, angle of 90 degrees. This is XL angle of 90 degrees. Right? So an inductor, the complex impedance of an inductor is an imaginary number, a purely imaginary number. Right? Purely imaginary number. This is XL 90 degrees. For a capacitor, we can do a similar exercise. We can do the same exercise. This is V, IC. (90 degrees), this is V over IC. Angle minus 90 degrees, this is XC. Right, so this is also a purely imaginary impedance, this time with an angle of minus 90 degrees. Right, so then once you have those complex impedances, things are really just complex algebra. Right, so you have RL, their impedance just adds. Right, so this is exactly the same as when you have two resistors, you have a real impedance. Now we're just adding two complex numbers. Okay, just adding two complex numbers. So there's a real part and imaginary part. The questions about this kind of operations? Similarly, when you have R and C, this is real part, imaginary part. When you have RL and C, again, you just add everything together. Okay, so this is all sort of fairly simple algebra, very simple algebra. So for this class, it's important to make sure you can do complex algebra either on your calculator or on your computer. Right? Most questions is, when you do computation, you have a bunch of complex numbers, but add them, multiply them, subtract them, divide them, and so on. So make sure you can do it. Right? Make sure you can do it. Let's say on your computer. Right? Make sure you can do this. If you're using a calculator, make sure you're doing a calculator. Your calculator can do complex algebra. Make sure you get the angle correct in the correct units. Okay, so in this class, we'll talk about, sometimes we'll talk about angle in degrees. Sometimes we'll talk about angle in radians. Make sure when you do the calculation, you do it in the correct units. And make sure you can do these. Okay. Right, so series impedance is easy, right? Just addition. So let's look at parallel impedance. Okay. So when we have parallel impedance, what happens is, right? So we'll try to derive a very similar equation as when you have parallel resistances. Right? So if you have parallel impedance, here the current is IR. So this is KCL, right? Kirchhoff's current law. The currents L add up. Then this is V over R plus V over XL plus V over XC. You can factor this out. This is V times 1 over R plus 1 over XL, 1 over XC. So the equivalent impedance, right? If you view this as one big equivalent impedance, then you have 1 over the equivalent impedance is 1 over R L plus 1 over C. Okay. Any questions about this? It's the same as the same as before. We have, let's say, 3 resistors in parallel. Right? So then the question about the grid. If you look at the grid, right, do you think is it more likely we're looking at things in series, or are we looking at things in parallel? Which is more likely?
Parallel.
Right, in the grid is much more likely if we look at things in parallel. Right, so it's just, for example, different houses are, in parallel with each other. Right, so that's sort of more likely to happen. So often in the grid, for convenience, we'll look at this 1 over Z instead of impedance, right? So this is our admittance, right? So this is the, just a shorthand. And the admittance is used because we really don't want to do fractions all the time, right? So we rather add. So when things are predominantly in parallel, it's often notationally more convenient to look at things 1 over the impedance rather than the impedance itself, right? So in this case, if you just look at 1 over things, then it's just adding, right? So we can define the same circuit taking the reciprocal earlier, right? Then just addition. Okay. Right, so this is more for notational convenience. Right? So often for things, if we work with a lot of parallel elements, we'll talk about admittance. But really, sort of these two things are equivalent. Just which one is easier to write down. In this class, we'll still be most time looking at the impedances, because we'll not talk about large systems. Most time we'll look at 1 or 2 loads. So then working with impedance is not so hard. But then if you take the next class in the next sequence, for example, we take 454, most of the times we're looking at Y rather than Z. Okay. We're looking at Y. Okay, so then the units for this admittances is just Siemens, right, or S. Right, so does anybody know another name for this units? That's a more interesting name. Right, so as we recall, for impedance for Z, this is in ohms. Right. Anybody know a more interesting name for admittances? Okay, so the more interesting name for these things is actually before, if you look at textbooks, let's say 20 years ago, before, so previously this was called, we had a unit of mho, which is just ohm written backwards. And the symbol was a backward upside down ohm. That's sort of the unit we had, right? So for example, when I was taking the class, we're still using mho, actually. That was a unit I used, talking about these things. But then people thought we should be, taken more seriously. Let's not create funny names and funny symbols. So now we use S, right? S is just 1 over O. But if you look at still some textbook nowadays, still uses this sort of funny symbol, upside down O, right? So that's for admittances as a unit. All right, so now we have, many, right? So now we can create, right? So now if you look at parallel impedance, so the question before was, is the angle positive or negative, right? Is it leading or lagging? That depends on whether the inductor or the capacitor is larger for a parallel circuit. So definitely you can create different angles, both positive and negative angles, by varying the sign of inductors and capacitors. So that happens in practice. You can often have, inductors and capacitors. Any questions about this?
I don't get the picture, the 3 pictures at the right.
Oh, you don't get 3 pictures? Okay, good. Right, so let's go through the 3 pictures. So the question, right, so the idea is looking at, if you look at a circuit like this, right? If you look at a circuit like this, and then let's say, let's do this slower. Okay. The idea is to say the following: if I have a circuit, so I'm going to replace that circuit with a big block, right? So we're going to have an equivalent impedance or equivalent admittance here. Then the question often comes up in practice is this more inductive or capacitive? Right? Does it look more like an inductor or more like a capacitor for this circuit? That have some, as we'll see later in this class, that have some implications to the operation of the grid, actually. That has some, right? So the way you determine this is, if you look at this resistor, right? So recall Y is a summation, right, of 3 terms, of the 3 terms. The idea is G is always 0 angle, right? So G has no imaginary part. So G is always 0 angle. So this comes from this resistor. Now you can look at capacitor and inductors. So a capacitor is plus J plus imaginary part. So this is your capacitor. This is capacitor. This is the inductor, right? So the 2 capacitor inductors are they're fighting each other, right? One's positive, one's negative. So what this being more capacitor or more inductive depends on which one has a larger value. Okay? Depends on which one has a larger value. Does this make more sense?
Let's make more sense. Thank you.
Yeah. Okay. So good. So now let's, yeah, go ahead.
Sorry. So in the middle case where BL equals BC, does it basically just act the same as if there was just a resistive circuit?
Right. They cancel exactly out. So electrically, you don't see them.
So when you're like doing math to solve those type of things, can you just ignore them and pretend it's just a resistor? Or
Sure, if they're exactly equal, ignore it. But the safer way to do math is just to plug everything into your calculator or computer, just let it do it. Actually, that's actually the safer way to do it.
So
But,
this is depend. This is
yeah.
depend on like the value of the impedance also.
Yeah, depend on the value. Yeah, depend on the
Okay.
value. Yeah, so that's a good question. That's a good question. So let's look at why in practice we may want them to cancel out, right? So why do we want them to cancel out? So the reason we have this sort of trick and we do this cancellation is the following. As if you look at the transmission line, okay, so this is actual transmission line you see, right? Let's say the overhead transmission line you look at. Okay? So this is actually a transmission line, you know, from somewhere, let's say Seattle to Belleville, we build a transmission line. If we model a transmission line, what does a transmission line look like? Anybody know? Right. So the circuit model for transmission line, there'll be some resistance for the line, of course, but then what else does the line look like?
Inductive, inductance, and capacitance. It's all three.
Which dominates? Is it more inductive, right? So the line turns out to be very much inductive. This is approximately just an inductor, actually. The resistance of the line is roughly not very large. For transmission lines, especially. The resistance value about 1/10 of the inductive value. The capacitive value is often very, very small. Okay? So the line looks like very much like an inductor. The line looks very much like an inductor. So from let's say the substation to your home, basically it looks like an inductor. Okay? The line to your home. So this is load. This is your home. Okay. So often we don't want very large inductive lines. So the line being very inductive can lead to some issues operationally. So often what you see as close to your home, you install a capacitor to cancel this out. Okay. That says install close to your home. So if you walk around your neighborhood, sometimes you'll see this sort of big box on some yards. So you see this sort of square box. So let's do not touch on the outside, this utility box. Often that's a capacitor sitting there trying to cancel the inductor out. So if you walk around next time, you can pay attention. You'll see this kind of boxes out there. Right, so that's when we try put a capacitor to ground, trying to cancel the inductance on the line. You want to basically make get more capacitive, get your load to be more capacitive.
What is the advantage of that? Is it like reduce the currents going through, or?
This boosts the voltage, makes your voltage higher. So over a long line, your voltage seems to drop. A capacitor will boost the voltage. We don't have enough math yet. We'll get there next class probably to see why this is the case.
Okay.
Intuitively, this puts your voltage up, right? So often, especially if the line is very long, by the time you get to the end, the voltage magnitude tends to be low. And one way to boost that up is put a capacitor there for support voltage. Yeah.
That's interesting.
So we'll see that when we talk about power. We'll see that when we talk about power, which is the next topic. But yeah, so next time we walk around, pay attention to this kind of boxes. You'll see there's fairly common, especially in more residential neighborhoods. You just see somebody's yard has a big box in front of it. That's a capacitor. That's for transformer capacitors in there.
So in a residential neighborhood, how big are those things usually? Like farad wise? No, like farad wise.
Right. So it's about let's say a meter by a meter, right? Roughly that size, meter by meter.
Yeah, no, sorry, the capacitor itself, like farad wise.
The capacitance in the microfarads, or hundreds of microfarads. It's a sizable capacitor. Right? Capacitors are really large things. Yeah, so it's a sizable capacitor. And
so you said like we have those capacitors to increase the voltage
yeah.
by the time like it gets to your home, but
right.
And is that also to like reduce like the reactive power and just increase like the like the average power. That's kind of what we talked about in 233, where like you reduce the inductive load to
Yeah,
increase power
right.
transfer. Is that
I
right?
understand that. The power transfer for us, once it gets to the residential neighborhood, you're not limited by the power transfer capability of the lot. You're limited by the voltage. So really for us, it's boosting voltage.
Okay.
Yeah, we're not limited, especially when you see those capacitors as not trying to improve power transfer. It's really to say your voltage is low, so I need more reactive power to boost up the voltage. Okay, good, right? So this is our capacitor. So capacitors are really useful devices. So anytime when you build a circuit, you see some problems, installing a big capacitor solves 99%, 95% of all your problems. That's actually true for all circuit design. Right? So anytime if you can put a big capacitor, things are nicer. Right? So that's we'll see this sort of again and again in the USR circuits. Okay. All right. So next, so if you think about what does reactive power mean, the next discussion is talking about power. Right. So this is a power. Right. So I work in power systems. Most of electric energy is talking about power. So what does that mean? Right. So what does power mean? So power fundamentally is voltage times current. Right? That's what power means at the end of the day. Right? So if you write out this instantaneous power, this is nothing but, so this is our power, V max, sine omega t, I say I max sine omega t minus a angle theta. So there's some generic angle theta. So this doesn't mean the angle is positive, but just some phase offset theta. So this is the instantaneous power. This is of course time dependent as multiplication of two sinusoids. The problem with thinking about power this way is this is a really complicated formula for power. Right? So it has a multiplication of two sine waves. Right? So this is not a very convenient way of thinking about power. Okay? We rather think of power as an average quantity and not a product of two sine waves. So a more convenient way of thinking about power is to say when you multiply two sine waves through some trig identity, it becomes this. Okay, so this is just a trig identity, become this kind of form. And then the nice thing is, I cannot talk about the RMS quantities for voltage and current now. So it's just V max times I max divided by 2. So we're going to put √2 to each of them. We're going to separate √2 to each of them. Cosine theta minus cosine 2 omega t minus theta. Okay. So this is VI. So these are the RMS values. And this is also nice is because when we talk about voltage and current, most times we do talk about them in terms of RMS values. And it turns out that's very convenient because when you talk about power, we want to talk about V times I. It turns out for sinusoids, when you talk about power, the V times I are the RMS values, right? So that's a really nice part of this. We talk about V times I, this is cosine theta minus cosine 2 omega t minus theta. So the first nice thing is now we can talk about RMS values. So we never need to talk about the peak values again. We'll talk about power or RMS, okay? Just RMS values. Right? But still, when we still have two terms inside the bracket, we still have two terms inside the bracket. So let's look at what to do with the two terms inside the bracket, right? So continuing with the equations, right? So to continue with this equations, if you look at this power, this rho, right? So this V times I, this is a Greek letter rho. This is a Greek letter rho. So this rho is, there's a reason we're not calling this P. Okay, so we don't want to use P as a symbol for power because we use P for something else. Okay? This is VI cosine theta minus VI cosine 2 omega t minus theta. And what we want is, we want to call this P because this is a constant, or rather this is time invariant. This does not depend on time. Okay, this is time invariant. So we want to call this P. This is the power we think of when we talk about, let's say, how much power consuming, or you're getting, you're paying your electric bill in terms of power usage. This is the power we think about. This is a constant. This is sort of a time invariant part of it. This is time dependent or time variant. This depends on time. Okay, this depends on time. And if you look at the two parts of it, then what happens is want to identify the power with P, but then we need to somehow characterize how large this time dependent part is. Okay, the time dependent part is, right? So this is time invariant, this is time dependent, but this is not necessarily zero mean. This is not zero mean. It's not yet zero mean. So what we want to do is we want to basically talk about sort of the constant part versus time dependent part. I want to relate this. So we want to relate this instantaneous power to the complex numbers we've been using, right? So again, we don't want to talk about frequency. We don't want to talk about omega or t when we talk about power, because we want to do everything from the complex number domain. We want to do everything as complex numbers. So let's try to relate these things. Let's try to relate these numbers. Let's try to relate these numbers to the complex numbers, to the phasors that we have. Okay, so let's try to relate them case by case. Okay? So if you have a purely resistive load, what happens is you have a V times I, and we have a 1 minus cos 2 omega t term. So this you can write as Vi minus Vi cos 2 omega t. And this is something that has zero average. There's something that has zero average value. Okay, this has something that has zero average value. Okay, and so for a resistive load, what we want to do is we want to say that. So this, right? So that's fine. So right. So if you look at things in phasor domain, or in the complex number domain, we have, for a resistive load, we have V times I. If you just multiply the phasors together, you also get, right? What you do is you get V angle 0, I angle 0. Since there's no angle difference, you also get V times I. So the idea is we want to relate what happens when you multiply the complex numbers together to the instantaneous power. Okay, so we want to make identification of this V times I with this V times I. Okay, Basically, we want to ignore the part that's sort of the VI cosine to omega t part. That's what we want. Any questions up here?
So the part of the right is gonna become 0.
So it's time varying, right? So it's not exactly 0, but we're gonna ignore it, right? So we're gonna think of as 0. That's our goal. Right? So we're gonna try to match and try to, in our mind, we're gonna think of that as 0.
Are these basically the steady state and transient state responses, or is that something different?
Not exactly, because everything is in steady state. Whereas this is actually not a transient, because it's the same sine wave just goes on forever. So it's not a transient. Rather, this is a constant value, right? This is something that's constant, v times I, versus something that's averaging out to be 0 across time. Right? That's roughly the idea. Right? So we want to keep one part, v times I, that's important. The other parts we don't care about for this. But it's not exactly transient. Right? This is steady state, but in some sense, we only care about the constant part for resistor. We don't care about something that's varying with 2 omega t. That's not something we care about. Okay, so this is for the resistive load part. We have 3 minutes, so we'll do the calculation for the inductive and capacitive next class. We'll do that next class, and then we'll extend this to a complex load. Basically, we'll identify what happens when you multiply complex number, the complex phasors together with the different terms in the instantaneous power. So this will set up something called an active and reactive power part. And then from there on, we won't worry about this omega t term in the power anymore. We'll just look at what happens when you multiply V and I as complex numbers together. Identify the real part and the imaginary part. Right, so we'll complete that sort of the beginning of next class. We'll complete the story. Okay, and so the homework will be posted tonight. Right, so we'll do every Thursday at midnight. So the homework will be posted tonight, and be due sort of next Thursday. And for me, as I will take a look at Discord servers to see sort of whether UW or our department has any official guideline about Discord servers.
Quick question.
Yeah.
So the homework is always due on Thursday next week's, right?
Yes.
Like the pattern. Okay.
Yes. Yeah. So homework is always out on Wednesday night, due the Thursday next week. Out on Wednesday night, due the Thursday next week.
Okay. Thank you.
Okay. All right. So no other questions, and I'll see you next Monday. Guys.
Thank you, Professor.
Thank you.
Thank you.
Thank you.